Hey, hello there. So today we have another binary search question, 658. Find k closest elements. We have a sorted array ARR and two integer values k and x. We want to find the k closest elements to this x reference number. The value x may or may not be in this array. We don't really care. The usage of x is to use it as a reference for us to calculate the distance between elements inside the array with that reference line. And we want to basically find the k elements that has the smallest distance. The result has been sorted order, and if there is a tie, meaning we have two elements from the sorted array that has the same distance with the reference number x. If we do have that kind of a tie, and we also have to make a choice between those two numbers, we would choose the smaller elements. So that's sort of like on the two kind of extreme sides, and if we have tie, we want to pick the smaller one. As an example, we have 1, 2, 3, 4, 5. The reference number is 3 and k is 4. So obviously, since that the number is inside the array, we would want to choose it, because by choosing it, the distance is going to be 0. It's the smallest that's possible. And then looking at the two numbers on each side, we have 2 and 4. Both will have the distance 1. That's the second smallest possible distance within this array. We will definitely pick those two numbers. So together we have already picked the top 3. We are missing 1. Looking at the remainder numbers, we have 1 and 5. Both 1 and 5 have a distance 2 with this reference number. And since we do have a tie, we want to choose 1 over 5 because 1 is smaller than 5. So as a result, we will return 1, 2, 3, 4. That's the first example. The second example, the reference number is smaller than the smallest. So it's just showing you that the reference number can be outside the array. Then we choose the 4 number that's as small as possible, since that x is smaller than the smallest. We choose 1, 2, 3, 4. So the brute force solution is basically just write a code that's sort of like a translation of what this question is asking. We sort the elements inside the array based on their distance with x. If we do have a tie, we then sort on the array's value, the element's value itself. So just throwing a customized comparator to first sort by the distance. After that, we sort by the array elements value. Then just using that, doing one sorting and take the top 4. We pretty much are done with that. So it's n log n time. And the other kind of situation, the other solution that we do is to pretty much if we look at the example that we worked through, we first thing we want to do is to try to find a number that's that's closest to this reference number, and then we do find some kind of symmetry around that number. And so the thing that we would do is to do binary search to find this number that's closest to the reference, and then have a window that's rather wide with 2k elements, k from left and k from right, and have that 2k plus 1 maybe kind of a window, and try to shrink that window down to top k. We can, iteratively looking at the leftmost and rightmost inside the window and decide which way we shrink the window to be as tight as possible with exactly k numbers. That if after that procedure, we will end up with the k smallest k closest elements to this reference. So apply binary search to find the closest element inside the array, then form a window of size 2k plus 1, k on either side, expand to k on either side, or maybe actually 2k minus 1, since that we are sure this number is, we only need k minus 1, so we can have k minus 1, expand k minus 1 on two sides, and try to shrink that to k minus 1 window to be exactly k. So that would be log n plus k. Those two are not optimal because it's only looking at the problem at sort of like a local level of the property. So we want to have some kind of bigger picture about this question. So there's no better way than sort of thinking about making a plot of the array against the the distance of this array elements with this reference number against the index. So let's say that we have a function that's just going to be the absolute difference between the array's element I and x. And if we plot this against I, let's just make a sketch plot here. So it will look like something that's starting to decrease. Maybe going up even further, and that's the case when x is within the lower bound and upper bound, the minimum and maximum number inside the array. We will definitely see this kind of turning point. The fi values will decrease and then increase. As another example, when if we calculate the fi, will be 2, 1, 0, 1, 2. So it's exactly the V shape with the 3 here being the the point where we can flip to have a perfect symmetry with this input example. Here we have a slightly different one because we kind of are having skipped numbers and stuff. So let's say that we want to find k equals 3 with this problem here, where the since the fi has already been plotted, we want to just take the the k dots that's as low as possible. If we work on the example with k equal to 3, we just take this 3 numbers. It's a continuous subarray, continuous window inside the original array. We just take this 3. If we want a 4, we move the line a little bit higher to include the one extra asterisk on the right hand side, and that would be a solution to k equal to 4 with this problem. If we want to do k equal to 5, we have to make a choice between this the left hand side one and the right hand side one. They are tied in terms of fi, and since that for the question's purpose we want the element that's on the smaller side, we will pick the one on the left. So that's the kind of the thing. So if we look at let's say go back to the window of size 3, we do see that it's kind of a symmetry, and we also notice the elements. If we compare the elements that that's the first element. We compare the first element inside the array and the first elements outside the array on the right hand side. This one that's there is a smaller than kind of a relationship compared to that one. If we want a window of size 4, we move towards right, and the first element inside this window is still smaller than the first element that's outside the window, the returning substring subarray. That's because if on the contrary the first element that's outside the window is actually smaller than this one, we're definitely gonna swap that by shifting the whole window towards right by 1. So it's guaranteed that the first element inside the window is kind of smaller than the first element on the outside the window. Just looking at this current example, if we try to have a window that's one size larger, we will actually choose this one, choose to expand the window towards left by 1 to include this one, because in this case, when we looking at the first elements inside the window and the first elements that's outside the window, it's equal. When we have equal, we want the stuff on the smaller side. So a little bit formally, if we define this kind of a relationship as a function gi, which is going to be the fi is smaller than or equal to fi plus k. When you look at this, if we're looking at a window size of 1, 2, 3, 4, 5, k equal to 5, in this problem here, the GI values would be the first one would be 0. The first asterisk, if we choose this to be the initial element inside the window, it will be 0. We call the GI. Then it will be 1, 1, 1, 1, 1, 1, all the way. How many elements we have towards the right, it will be how many ones here. If we have some asterisks that's actually even higher than that, it will just generating another 0 on the left hand side. So this GI is actually a sorted sequence, so we can apply binary search on the GI value to find the I, which is the starting location, starting index for the window of size k. So after observing this, we can just apply binary search to solve this problem entirely without any kind of a window shrinking, or and it's also much better than the sorting, naive sorting. So yeah, just gonna after this analysis, just gonna code this up. It's gonna be log m minus k, because the window size has to be at least k, so the upper bound is slightly tighter, but overall it's log n. Lower bound and upper bound to be array size subtracted by k. We got an m value. This m value is going to be the function as the I here. It's going to be the starting index for the window. Just going to put a little note here. I'm going to put that inside the binary search. Then we're just gonna compare that. The mass is fi, which is the distance from the x to array of I, is smaller than or equal to. We want to find the 1, so we're gonna compare the opposite and try to bump up I. So that's gonna be x subtract fi arr m is if it's larger than m plus k subtracted by x. If this is the case, that means we're looking at these two zeros here. We want to increment m lower bound to be 1 larger. Otherwise, we want the upper bound to be smaller. In the end, we'll just return a slice of this array. It's vector, integer, from begin plus L, starting from L, and expand towards right by k positions. So that's the code. Let's try run through some examples. Okay. Yeah, it's working and pretty fast. So that's the binary search solution to this question. Yeah, that's it.